right, here we go. This is the second video of section 3.2, but actually it's the um, first video using the actual notes that I gave you to fill out here. So we need to understand that there are two possibilities whenever we're given a formula or equation. There is explicit form, and explicit form means we definitely know, it is clear that y is equal to all of this. And then we can also have what's called implicit form. And as you can see in implicit form, my equation is not solved for y. So I don't know what y equals. I don't know what x equals because all my terms are all mixed together. However, this is a perfectly legal equation, right? And if I had Desmos, I could graph this and see that it does create a graph, or I could graph this and I could see that it does create a graph. So equations, they they give us information, but the way they're given to us, whether it's explicitly or implicitly, is going to determine my next step in finding the derivative. So remember that when we're finding the derivative, we've been using explicit form. So if we're finding the derivative of y, we've been using this symbol, dy dx, as saying the derivative of y with respect to x. And we've been using that to figure that out. But if we're not in explicit form, then what can we do? And so just to kind of make sure we understand the idea, we'll do example one before we start using implicit differentiation on its own. So when I look at example one, we have three different situations. So the question is, do I have an implicit or do I have an explicit setup? And so when I look at this first part, or letter A, I should say, when I look at letter A, I'm taking the derivative of this with respect to x. And so I ask myself, is this expression in terms of the variable that I'm taking the derivative with respect to? Well, yes, because I'm taking the derivative with respect to x, and my expression has x's and only x's. So therefore, this derivative is just going to be 3x squared by using the power rule. This is a normal, quote unquote, normal derivative. But when I look at letter B, this one's a little bit different because I'm taking the derivative with respect to x, but my expression is in terms of y. So it's almost like the example that we saw in the first video where this whole thing is a function of x that I don't know what that function is, but I know that it's being cubed. So just like in the initial video, what we're going to have to do is identify that this is the outside function and this is the inside function. So we're going to take the derivative of the outside with the inside still in it times the derivative of the inside, which I'm going to call dy dx. You can also call it y prime, but you'll find out pretty soon why I prefer to use this Leibniz notation, dy over dx. So notice the difference. Here, the variable of differentiation matched the variable of the expression, so I just took the derivative normally. On example B, the variable of differentiation was x, but my expression was in terms of y, so I had to use a chain rule because I'm treating y as a function of x. So it's almost like I have an inside function y being taken to the third power. So I took the derivative of the outside with the inside still in it times the derivative of the inside. I did the chain rule. So what happens when I get to things like letter C? Well, I have to use the rules of derivatives, right? So the rules of derivatives say if I'm adding two things, I can take the derivative of the first part plus take the derivative of the second part. Well, if I look at the first part, these two are matching variables. The variable of differentiation matches the variable of the expression. So I'm just going to take the derivative of x, and that's going to be 1. And I'm going to add that to whatever I get over here. But when I look over here, the derivative of differentiation is x, but I don't have an x, I have a y. So I have to treat that like a function, like an inside function. So I'm going to take the derivative of the outside. The derivative of the outside would just be 3 times the derivative of the inside, which would be dy dx, right? Because if I have, so this is this part, and I guess I'll, oh no, I'll do it in a different color. This part is like saying, what's the derivative of 3x? Well, the derivative is 3. Well, what's the derivative of 3y? Well, the derivative is 3, except I'm treating y as a function, so I got to take the derivative of that inside function, and that's why I have this extra dy dx. So again, we're going to have to be very careful when we're taking the derivative implicitly, because we have to pay attention to the variable of differentiation. What are we taking the derivative with respect to? And the variable of the expression, because one of them is the variable, but the other one is a function of the variable, or I'm going to treat it as a function of the variable. I'm going to slide it over. And we'll do one more here. We're going to take the derivative with respect to x of x times y squared. These are two different things, right? X is the variable, y is a function of x. So because I'm multiplying two different things, I have to do a product rule. So I got to find the derivative of the first times the second, plus I got to find the derivative of the second times the first. Well, the derivative of this first part is pretty straightforward. The derivative of x is just x. I'm sorry, the derivative of x is just 1 times y squared. But over here, the derivative of y squared, I have to treat this as an inside function. And that would mean this is my outside function. So my derivative would be 2y. The derivative of y squared is 2 times y times the derivative of the inside, which is dy dx, times the x that was part of the original formula. And so this would be the complete implicit differentiation that I would need for this expression. I took the derivative of the first, 1, times the second, y squared, plus the derivative of the second, because this is x and this is y, that would be 2y times dy dx, times the first, which is x. And I would leave it like that. I mean, I guess you don't have to put the 1. You can just put y squared. Oops. You can just put y squared, I guess. I wouldn't factor out a y. I would just leave it like that. So the moral of the story is we're heading towards situations where we're going to have equations that are not just in terms of one variable, but in terms of two. I'm going to have to pay attention to the variable of differentiation, this dx on the bottom. Sometimes it's dx, sometimes it's dt, sometimes it's dy, and that's going to be our variable. And then whatever isn't that letter, we're going to treat as a function of that variable. That's what's going to be a little bit different with implicit differentiation, but all of it is based off of the chain rule that we've been practicing.